Welcome back, everyone. In this lecture, we're going to focus on creating the model and training the model. And we're also going to emphasize the aspects of the model that you can play around with and edit versus the aspects that, based off the constraints of your problem, should essentially always be fixed. Okay, let's get started by heading back to the notebook. All right, so here we are at the notebook where we left off last time. Just as before, when we're creating a model, we're going to say from TensorFlow.keras.models import, and we'll import a sequential model builder. We'll still build out our models sequentially by adding layers. The main difference is going to be the kind of layers we actually add to this. So we will say from TensorFlow.keras.layers import, and we're going to import a dense layer just as we did before, but also a convolutional layer for handling 2D images, which is conv2 capital D, and then also max pool 2D, and then eventually we need to flatten out these images to feed it into our final dense layers, which will actually perform the classification. So there's a special flatten layer for that. Okay, so let's begin building out our model, and we're going to focus on a couple of parameters throughout the actual adding in of the layers. So, just as before, we start off by building out our sequential model. Then, the next thing you need to do is typically, for a convolutional neural network, the first layer that it encounters is a convolutional layer. So we will say model add, and I'm going to add in convolution, 2, capital D, parentheses, and if you do shift tab here, it'll show you the documentation string. Remember, we've already imported it, and we have parentheses here, so I can see the documentation string. Otherwise, just call help on the actual class call. But there's 4 main parameters that I want to essentially explain to you here. And that is the filters, the kernel size, the strides, and the padding string. Now, we actually already understand filters, kernel size, strides, and padding theoretically based off the theory lectures that we just went over. The main thing we have to figure out is what values do I choose for this? And a lot of times there's no 100% correct answer. It's based roughly off of the input data that's coming in. So, really typical values for number of filters is the more complex the data set, so essentially the larger the images, the more variety in images, and the more classes you're trying to classify, then the more filters you should have. And it's really common to choose filters based off powers of 2. So a very common starting point for number of filters could be something like 32. But you can imagine that if you're dealing with a really complex set of really large images, and maybe you're trying to classify something like the number of or the types of road signs. So you have a stop sign, a yield sign, a turn left, turn right, and you have a lot of classes. It probably makes sense to then add a lot more filters to try to begin to understand or have your convolutional neural network understand the various shapes that come with all these different signs. Now, in our case, we have really simple data set of just handwritten numbers where we have 10 classes. So filters with a power of 32, or excuse me, with a chosen value of 32, is a good step to start at. The next thing we need to decide is that image kernel size. And again, typical sizes of image kernels are something in the range of 2 by 2 or 4 by 4, and then you can keep expanding it based off, again, your data. A good starting point for this is 4 by 4. Okay, so what about the other 2 parameters that we discussed in theory? So the next one is the size of the strides. And there's 2 dimensions here because you can stride in both X and Y. And recall that the stride is basically how big of a stride are we taking as we're moving the kernel along this image. In our case, the test images are actually pretty small. They're only 28 by 28 pixels. And since our kernel is 4 by 4, we can actually then determine how long of a time, or essentially how many pixels is it going to take to go over by just saying 28 divided by 4. We can get an idea of that scanning of the image. If you're dealing with really large images and you're still dealing with a smaller kernel, you would probably want to expand on that stride size. In our case though, we'll go ahead and leave it of the default of just 1 by 1 pixel. So essentially it's just striding along by default pixel to next pixel to next pixel, etc. And then the next one is padding. And if you take a look at padding, it's either valid, so it's a string code valid, and if we scroll down here, it'll say that it's either valid or same, and those are your only 2 options. So what do these strings actually mean? If you do a quick Google search for what is the difference between valid and same in the string, you get this nice link to a Stack Overflow post that basically talks about what's the difference between this same and valid padding. And this actually links to max pool of TensorFlow, but it's the same code for Keras as well. And if we come down here, there's an example here talking about same versus valid pad, but I like some of these more visual examples, and probably the clearest explanation is if you scroll down here, the clearest to me was essentially this quick explanation right here. And it's towards the bottom. All of these explanations essentially say the same thing, but the string valid basically tells you do not apply any padding. What we're going to do is we're going to assume that all dimensions are valid so that the input image fully gets covered by the filter and stride that I specified. So is that going to be the case here? Well, let's think about this. If I have 28 and I divide it by 4, that goes evenly 7 times, and I'm only doing a stride of 1. So if I just move my kernel, which is 4 by 4, along my 28 by 28 image, I shouldn't have a need for padding because I won't actually overshoot because I fit perfectly with a stride of 1. But if this begins to give out decimal numbers, you may end up encountering some errors because you're overshooting. And in that case, we have to decide, are we just going to drop those points? Are we going to pad it with zeros or ones, etc.? And so then what we do is we'd have to specify the string same. So what's nice about same is it automatically figures out what the padding should be. So what happens here is it's going to apply padding to the input only if needed, so that the input image gets fully covered by the filter and stride that you specified. So for example, if we decided on a stride of 1, that ensures that the output image size is the same as the input image. Okay, so there's lots of other explanations here, one that goes into the math of it, and another one here that shows you essentially what this is doing through a little bit of kind of a visual explanation. So I'd encourage you that if you just Google search, if we go back here, valid versus same padding, you get a lot of outputs here. Okay, so again, you can look at those explanations. In our case, we'll just go ahead and keep the default, which will work fine for us in our case, where we just have padding is valid. Okay, so that's our filters and our kernel size. The couple of things we need to now add in is define what is the input shape that we expect here. So that's going to be input shape is equal to, and in our case, this is just the input shape for a single image, which is 28 by 28 by 1 color channel. And then finally, we choose what kind of activation function do we want. So the activation function we'll choose is rectified linear unit. So we'll say activation is equal to rectified linear unit. Okay, so let me just put this all on one line here. And I can zoom out just a little bit so we can see the whole call. Our convolutional layer has some determined number of filters, a kernel size. If we want, we can specify padding, but in this case, we didn't have to. And then we can specify the input shape and the activation function. Okay, so that's our convolutional layer. After your convolutional layer, you should have a pooling layer. We will say model add, and here I will call max pool 2D. And the main thing to choose here is the pool size. You can also add in things like strides, padding, etc. But really, the key factor is pool size. And we'll go ahead and just do a pool size that's half of our kernel size. 2 by 2 is a really common metric here. So we'll go ahead and just say pool size is 2 by 2. That is the default, so I technically didn't have to specify that. But I do want the visibility of what I'm doing here. Okay, now we're going to just keep it as having one convolutional layer and one pooling layer. So a very simple convolutional neural network. Now what I could do is keep adding convolutional and pooling layers, and we'll do that later on for more complex images. But right now we'll just keep it simple, one convolutional layer, one pooling layer. After your series of convolutional and padding layers, you'll need to flatten out the images. So when we're flattening out the images, that essentially means take a 28 by 28 image and then flatten it out to be just a single array of, in our case, 784 points. So take one of these 2 by 2 images and then flatten it out into an array of 784, which is 28 times 28. So we can do that by simply saying model add, and then we flatten out the image. Once we're able to flatten out the image, what we can do is we can start adding in our dense layers. And it's usually a good idea to add in one final dense layer that more or less matches the same scale of this. So the scale should be somewhere between 0 and 1000. We'll go ahead and say dense, and we'll keep kind of the power of 2 theme here, and we'll say 128 neurons. In this dense layer, activation is equal to rectified linear unit. And if you want, you can keep adding dense layers, but eventually we have our final output layer. So how many neurons should be in my final output layer? In this case, for classification, I should have 1 neuron per class. So that will be a dense layer with 10 neurons. And in this case, I also have to think of my activation function, which should be for a multi-class classification problem, not a binary class, but a multi-class, should be the softmax activation function. So again, it's going to be softmax because this is a multi-class problem. Then finally, I'm going to compile this. So we'll say model, compile, loss is equal to categorical cross entropy. Categorical cross entropy because it's a multi-class problem. The optimizer, we'll go ahead and choose Atom for our optimizer. And here, if I want, I can specify additional metrics, which is actually something we haven't seen before. But I could say, go ahead and add in some additional metrics. Typically what we do is we use loss as our metric, essentially the loss calculation from our loss function, which is categorical cross entropy. But something I could do is I could also keep track of something like accuracy. And if you want to check out what string codes are available to you or what metrics are available to you, you can go to keras.io/metrics. So if I go ahead and copy this and then paste it here to the Keras documentation, it'll actually show you the available metrics. There's accuracy, binary accuracy, categorical accuracy, top K, etc., clone metrics, and you can even create your own custom metrics. So there's lots of options here that we can keep taking a look at. So we'll go ahead and just choose accuracy, essentially the accuracy across all categories in our case, and we'll leave it as such. We'll still be able to calculate loss, but this is just another metric that we can keep recording during training. We'll go ahead and compile the model, make sure we didn't commit any typos, and we're good to go. All right, so I want to quickly highlight what can you play around with and what has to be set. Let's start off by discussing the parameters that are fixed and should be determined by your actual data set. Those parameters are your input shape. The input shape should essentially match what an image is going to look like. In our case, it's a 28 by 28 one color channel image. This input shape parameter is determined by your data. After your convolutional layers and your pooling layers, you will eventually have to flatten out your data. So this is another parameter, essentially a layer, that should be somewhere in your network. Then, the last couple of parameters that you will edit and should be set based off your data is this final dense layer. This dense layer should be equal to the number of neurons to your classes. So we have 10 possible classes, the numbers 0, 1, 2, 3, all the way to 9. So I should have 10 neurons here, and the activation function should then be softmax. If you were dealing with a binary classification problem, such as just an image of a cat versus a dog, then this would be a binary classification with just one neuron output with an activation of sigmoid. And then the other thing that's defined by your problem is the type of loss, and then here in our case, it's categorical cross entropy. Okay, now the things you can play around with are several here. You can add as many convolutional and pooling layers as you want, and then within those, you can play around with the number of filters, the kernel sizes, as well as the pool size. And you can also play around with the padding. Then after that, after you flatten it out, you can play around with the number of dense layers as well as the number of neurons in those layers. And typically, people just use kind of one dense layer, maybe two after they flatten it out. They don't have that many dense layers after flattening it out. Most of the work for image data should be done by the convolutional and pooling layers. Okay, so I just wanted to have that brief discussion highlighting what is available to you to play around with and what should be set by your data. All right, now the last thing we want to set up is training the model. To make sure we don't need to worry about choosing the number of epochs, let's go ahead and set up an early stopping callback. We will say from TensorFlow.keras.callbacks, go ahead and import early stopping, and then the early stop will be equal to early stopping. We decide what we want to monitor. By default, we monitor validation loss, but keep in mind, the other metric we could be monitoring is validation accuracy. Because I added metrics accuracy here, I could say val underscore accuracy as my monitor device. But we'll go ahead and keep it to the loss that's output by categorical cross entropy. And then we specify some patients. So we can specify something like patients 1 or patients 2. We'll go ahead and just set it to patients 1, so wait 1 epoch. Run that, and now we'll say model.fit, pass in our training data, and then for Y, recall we want to pass in the categorical version of these labels. We'll set epochs to something relatively high, 10, and then we need to make sure we also pass in our validation data set. So that's going to be X test, and also this should also be categorical, Y cat test. And then finally, to make sure we actually have the early stopping, we'll say callbacks is equal to early stop. Okay, let's go ahead and fit that model, make sure we didn't make any typos above, and it looks like it's working out for us. You can already see we get a very high accuracy right off the bat. This is a pretty easy data set to work with. Okay, so coming up in the next lecture, after we're done training the model, we will evaluate the model's performance. I will see you there.